Here I'm going to attempt to explain a little bit more about the calculations aspect of the emission spectral lab. In this experiment, we will be measuring the lines from an emission tube. It'll be sort of centered, and we're going to be looking through it through a diffraction grating at some distance. So, as you've done in lecture, you've looked through light through a diffraction grating, which is kind of like rainbow glasses. And what it does is it takes your one colored light, so we have our light source sort of in the middle, and what it does is we see the individual colors on each side from that light source. So the diffraction grating sort of like splits up those lines, and so we can see the individual photon colors. Our goal in this lab is to determine what the wavelengths of these specific colors are. So here's sort of like two different views, if you will. So if we are staring here and our diffraction grating is here, and we have this distance from the diffraction grating to the light source, there'll be the line that we care about sort of on both sides, and it'll be equidistant if everything's perpendicular. We'll see the same colored line on both sides. So, for example, we'd see a red line over here and a red line over here, and the distance between the light source and the red line is the same on both sides. The wavelength of that particular color of light is a function of d, which is the distance between the lines and diffraction gratings, so it's a constant. It's very easy to find, times the sine of theta over 2. And theta is the angle between the line on one side, or diffraction grating, and the line on the other side. So theta is this whole angle. So we are trying to calculate wavelength, and so we need to know what the sine of theta over 2 is. So we have some trigonometry we've got to deal with. So here is another way of our picture, and we're going to label some of the pieces. So we're going to say that x is the distance between the light source and the respective line on both sides, and then we're going to call the distance y the distance from the light source to where the diffraction grating is. The angle theta is this whole angle from the line on one side to the line on the other side, and we're going to cut that in half, and we're going to talk about theta over 2. And the reason why we're going to talk about theta over 2 is, well, we need to know the angle of theta over 2, and the other thing is that when we cut this in half, we kind of flop it over, so we do this sort of like this rightmost triangle. It is a right triangle. And if it's a right triangle, we can exploit our trigonometry rules that we learned back in geometry class. To get our wavelength, we need to know the value of the sine of theta over 2. That doesn't mean we need to know what the angle theta over 2 is explicitly. We just need to numerically know what this relationship is. So we know that sine is the opposite over the hypotenuse, and the cosine is the adjacent over the hypotenuse, and tangent is opposite over adjacent. What we're going to do is we're going to set up our experiment whereby we can very easily, for each individual line, measure the value of x and measure the value of y. Be very simple, and you don't need to worry about that. Just at this point, trust me that when we're in lab, measuring x and measuring y is going to be very easy. So we'll know those two values. Knowing our relationships of our trigonometric properties, if I know the value of x and I know the value of y, I know that the angle for 2 is equal to the inverse tangent, or the arctan, of the value of x over y. Because the tangent of theta over 2, the tangent of this angle, is the opposite over the adjacent. So, if I know the value of x divided by the value of y, I know that ratio, I take the inverse tangent of it, that will give me theta over 2. Do I care about theta over 2? No, I need to know the sine of theta over 2. Well, okay, so to get the sine of theta over 2, I simply have to take the sine of the arctangent, right? Notice that there's these little braces. So in here is the arctangent of x over y is equal to theta over 2. So that'll be my sine of theta over 2. So in our spreadsheet, if I have the value of x and I have the value of y, the way I would code in to get the sine of theta over 2, it is simply equal to sine, open parentheses, a tan x slash y, close parentheses, close parentheses. This is the code for the sine of theta over 2. To get our wavelength, we simply have to take this value, which is our sine of theta over 2, and multiply it by d, which is our constant. That's the math. Well, that's the hard math. In this experiment, you are beginning wavelengths of all lines in all elements. So you're getting the wavelengths of the 3 lines in hydrogen, you're getting wavelengths for 3 lines in mercury, and 6 lines in helium. So it's a total of 12 lines that you're measuring. For the non-hydrogen lines, meaning for all the lines for mercury and all the lines for helium, you're going to calculate a percent error between your value and the accepted value. As part of your pre-lab, you have to go and search out the wavelengths, what the lines are supposed to be for helium and for mercury. You're going to compare those known values to your line's wavelength, right? So you're just getting the wavelength from the Bragg equation, the equation on the previous slide. And then you can calculate a percent error. And here's the formula for percent error. For the hydrogen lines, so there are 3 hydrogen lines that you have, you need to actually calculate the initial n value. So for hydrogen, remember, we have this equation that relates the energy of a particular photon and the initial and final n states of that transition. For this experiment, n final is equal to 2. So that means all of the lines that you see are from some higher energy state coming down to n equal 2. So nf is equal to 2 in this experiment. So we're going to be calculating the wavelengths of all the lines. So we're going to calculate the wavelengths of the hydrogen lines. And from the wavelength, we can convert that into an energy. And from the energy, we plug it into the Bragg equation. If we know the energy, because this E is the same as this E, it's the energy of the photon. If we know the energy of the photon, which we calculate, and we know NF, that's 2, we solve this equation, we can solve for Ni. And remember, this equation has a sign convention. So the energy in here can be positive or negative, and it needs to be negative when we use it because these are emission spectra. So the photon is being given off, and so when we're going to calculate a positive wavelength, and we're going to calculate a positive energy here because of these relationships, but when we plug this energy into this energy, we have to change the sign, we have to make it negative. If we don't make it negative, we're going to get a nonsensical answer for n sub I. Good luck.